So thanks for the opportunity to present here. I came back from Davis 3 months ago, and I started a new lab at the Water Institute in Sde Boker. And I worked with some of the researchers here also doing my PhD, so it's nice coming back. And this seminar will be a bit different from what how usually seminars are given. I will talk mainly about like a tool or a method. You decide how to call it in the end, and I will focus again on the technical issues of this tool, which are called open source hardware. And I hope that in the end of the presentation, you will understand why this tool might help you do better science. And this will be the first part of the seminar. And the second part will be some more detailed examples in which I will show how actually this tool can do science, at least in my case. So I will say open source hardware. Sometimes I will say open source sensor, sometimes a low-cost sensor. They are all, for this seminar, they're all under the same definition. And I will start. Why use open source hardware? So in my opinion, it's mainly about the sensors. You can buy cheaper sensors, and you can build your own solutions for like specific needs in your research. Now, lower cost of sensors is not a main objective when we are conducting science. But if we have cheaper sensors, we can buy and install more sensors. And I would say 10 sensors at the price of one. And when I'm saying sensors, it can be whatever you are measuring. It can be temperature, relative humidity, CO2, oxygen, radiation, and so on. But once I have 10 sensors, and until now, let's say I bought only like 5 because this was the budget, but now I have like 50, I can really get a better understanding of what
Excuse me.
Yeah.
I don't know what are open source hardware.
So that's the next slide.
Because you say, okay.
Yeah, I will talk about it. But the first, like I'm trying to say why use it. So it's about cheaper sensors, and cheaper sensors can give us better capabilities, better measurement capabilities. And now, for example, if you're measuring gas transport, if we have one CO2 sensor in a room, it's hard to say how the gas is moving in the room. But suddenly, if we have 20, we can understand, or we can try to model the phenomena better. What is open source hardware? And from your comment, I understand this should be at the beginning, and in the next seminar it will be like that. So open source hardware is hardware whose design is made publicly, meaning in the internet you can find the design, how the chip is built. You can copy it, and that's okay to copy it because that's the idea of open source. You can use it for your needs and so on. Very similar to the concept of open source software, let's say Linux, which is more I'm guessing more common. People are aware of open source software, but open source hardware is a newer field, which the main driver is not the scientific community. It's what is called the maker community. People that are just sitting in their houses or in high school students in robotic teams. They just like to build stuff. And once they are building something which is successful, usually they will give the knowledge online how to duplicate it. Two main examples of open source hardware. First is the Raspberry Pi, if you heard of. It's like a low-cost computer. And the other one is the Arduino board. This is one type of a board. From this, with a few additional components, I can build a very cheap data logger. And instead of using like people that measure environmental parameters in science, usually use the CR1000 or the Campbell Scientific data loggers. So in Israel, a CR1000 data logger, which most of us, I'm guessing, are using, it's roughly like 15,000, 20,000 shekels. And this data logger can be a few hundreds of shekels. Now, of course, the high-end data logger has better capabilities, but for 80% of what we are doing, this is more than enough. And the additional features of a high-end expensive data logger are more than what we need. Where can we buy these sensors? Because, for example, going back to the data logger example, if you want to buy a CR1000 from Campbell Scientific, we know there is a provider in Israel, only supplier, and you buy from that company. But when you were talking about low-cost sensor, you can buy it from AliExpress, Amazon, eBay, whatever, where you do your online shopping. And I'm showing this slide because this is the original Arduino that was developed by the company 15 years ago. It's a bit hard to see due to the focus, but this costs $20. And there is another company that does exactly the same. They're actually copying the design because they can, and it's allowed. They're doing exactly the same, selling it like at a lower cost. And according to the ratings, you can see people are preferring the lower cost. I'm just showing this example to emphasize that in the end, it's okay to copy, and that's the idea. Like someone invented something and you're taking it to the next step. They will give credit to this company, but they're still selling the same product. But this is the hardware which you can use to build data loggers. And now I'll go to the sensor, because in the end, this is the objective. We want to measure environmental parameters. And this is one example for a temperature, relative humidity, and pressure sensor, roughly $20. Now, this is from a company named Adafruit, which is when you're buying cheap sensors, like you're buying everything from AliExpress, for example, sometimes you can get products that are not good enough. But when you're buying from companies that manufacture open source sensors, but they are like legit, solid companies, and there are a few in the world, you can be sure that although the price is cheap, the sensor itself is good enough for scientific objectives. And this company, for example, the Adafruit company, they're not building the sensor. They're taking a well-known sensor. This sensor is from Bosch and integrating it into a board that they designed and selling it. And because it's there are a few companies that really want to help us use this sensor because in the end they want to profit. They're also providing a guide how to build it, meaning they guide you step by step how to take it from the box, how to solder the sensor, how to connect it, how to upload the software, which is important because for most of us which are not electrical engineers, if we will not have this detailed step-by-step guide, we will not use it. So I'm showing where you can buy it and how you have the resources to actually use it. And I'll jump into several examples in which I used low-cost systems for my research. And we'll not talk about the science behind it, but I'll talk about the concepts. So this is the first example, which we developed what is called the e-greenhouse together with a team in Oregon State University. So you can see here different sensors. This is, for example, a CO2 sensor, which costs like $60. Temperature relative humidity sensor, the brain, which is the microcontroller, which is our data logger with an SD card. And all of this costs roughly $300. It can move or be stationary depending on the needs in a greenhouse. And suddenly you can get the microclimate inside the greenhouse, the CO2 concentrations, the temperature, if you want radiation, and so on. And everything is not only logged inside the SD card, but it's also being transmitted using cheap wireless protocols and being pushed to the cloud, so you can sit in your house and actually understand what is happening in the greenhouse. Now, this is not something new. Like there are companies that manufacture similar solutions, but the problem is that they are not doing it in $300 because they want to make profit. And if you need to pay a few thousands of dollars, usually you will not use this solution unless you have the budget for it. But once you reduce the price dramatically, you can suddenly install more greenhouse houses and really understand and let's say compare situations and so on. So this is first example. Another example for my postdoc at UC Davis. This I'm calling like a hybrid approach. Why a hybrid approach? Because I'm using sensors that are, let's say, more commercial standard sensors like this soil moisture sensor. But the sensors themselves are connected via cables to an underground node, which is low cost. You can see here in this picture. And inside this underground node, you have a microcontroller, which again, it's the brain taking all the sensors measurements, a power relay which closes the power for all the sensors when you are not measuring, a small battery that can last, due to this power optimization, a few years. And everything is being measured here and transmitted wirelessly below ground to an above ground hub. This specific solution solved the problem, the challenge that we had in a lot of our research areas in at UC Davis. These are like farm agricultural areas. And once you install an experiment, the farmer cannot get in with the machinery because you have a lot of cables. So this reduces this problem. And again, there are solutions you can buy from companies, but once you do it yourself, and like this costs, if I remember correctly, like $80-$70, and the same goes here. And suddenly you have a solution that is cheap and really sustainable for like a lot of years. You can install a few of these underground nodes.
What is it called? VWC?
Soil moisture, volumetric water content. Yeah. So this is like the commercial sensor, but all the other components, meaning these two sections, are cheap and you can do it by yourself. Now, this is a successful development. So the next step was to publish it. In our case, we are publishing, of course, in scientific journals. And in the publication, we also provide a step-by-step guide how to actually, from where to order, how to install it, how to connect it, how to solder, how to program it, so the end user can use it. Another example, here we developed a low-cost flux chamber. If you're measuring greenhouse gas emissions, you have a few techniques that I'm guessing most of you are aware of. One is the eddy covariance, and the other one is the static chamber approach. And in the static chamber, without going into the details, but you put a chamber, it can be like whatever size, or there are like certain sizes, but you put it on in this case, it's on the water surface, but you can put it also on the soil, and you're waiting, like once the chamber is on the soil or on the water body, you're measuring the buildup of CO2 inside the chamber, and from the buildup, you can calculate the fluxes. Now, this method is not new, and it's been used for a lot of years, but in most cases, the way to measure the buildup of the CO2, you're using pipes that are sucking the air into a gas analyzer, and this will give you the CO2 concentration. Now, this is a very expensive device, but in the last few years, there was a development of new CO2 sensors from a different area of interest. Because of the COVID, a lot of companies tried to install CO2 sensors inside rooms like that. And if the CO2 concentration is going up, it's a sign that you need to ventilate the room. So a lot of companies started to, okay, who will build the cheapest CO2, which will sensor that will still be valid with reasonable accuracy. But some of them were actually good, and some of them we can take from like settings like here and use them for research. So I took this sensor, which is like, it's a bit hard to see the scale, but it's like a 3-centimeter sensor, put it inside the chamber, and now you have in real time in the chamber, without the need of a pump and a very expensive device, you have CO2 readings. And you can see the results in this case. This is CO2 versus time. The green circles are 1 per second measurements of the sensor inside the chamber, and the orange circles are measurement using the very expensive device. Again, I'm not going into the details, but the slope is pretty much is very similar, and which validate our method. And this system costs $200. And when a gas chamber with the measurement costs $200, you can duplicate it and install it in a lot of different settings, in soils, in aquatic bodies. And this is what I'm doing now with collaboration in the Kinneret. And this launch box is just the data logger using the hardware I presented at the beginning. And it's in a large launch box because we want to do it waterproof, of course. So this is another nice example. And now we'll use this. We're planning to install 10, 20, 30 chambers in the Kinneret to really try to understand the heterogeneity of emissions inside the lake. I will not go over the methane emissions because in this case, we also did the same trial, but with a CH4 sensor, but it wasn't that successful. So for CH4, we are not there yet. And maybe the most ambitious trial that we did, and this was in UC Davis. So I said there is the flux chamber method to measure greenhouse gas emissions. The other method, which is more, most of the people will say more advanced, is the eddy covariance flux tower. And here we said, okay, we have these chip sensors. Let's see if we can compare different chip sensors to a CO2 IRGA sensor, which is like the benchmark for CO2 when you're using eddy covariance. And we put these local sensors inside the radiation shield and just compare between them. Now, the big challenge here is if in the flux chamber I can use a measurement of 1 per second, 1 per minute, it's good enough. When you're doing the eddy covariance method, you gotta have a sub-hertz measurement resolution, meaning you need a sensor that can measure, for example, 10 times per second. And this is what this very expensive gas analyzer does. In our case, in these sensors, you can measure, go down to like once per second or something like that. So for eddy covariance, it's again not good enough, but I'm saying yet, because this field is evolving all the time. And if I'm using these sensors, next year we'll have a better sensor that maybe can go with a resolution of sub-hertz measurement resolution. I will show just a comparison between the results of the expensive one and the low-cost one. So the red, you can see the $50 sensor, and the black is the LICOR gas analyzer. The y-axis is CO2 over time. And you can see pretty much we are on the right track. The trend is good. So it's, in my opinion, it's a promising direction to go. Another nice example, there was a mask developed. It's a bit of a weird story. The San Francisco Opera during COVID asked from some researchers in UC Davis to develop a mask that you can sing opera with the limitation of COVID. So they developed a mask, like a very unique design. Everything was okay, they could sing, everything is okay, but there was the concern of once you sing inside the mask, there is a CO2 buildup in the mask, which over a few, I don't know, half an hour of opera can maybe problematic for your health. So how do you measure CO2 inside the mask? Using the regular commercial sensors, it's a bit problematic because it's expensive, but that's not the reason, mainly because it's bulky devices. So we said, okay, same sensor again, let's just put it inside the mask. It's a small sensor, 3 centimeters, and this is what we did. And you can see here from the result, for example, it's a bit hard to see, but the red, this is CO2, the red line is while the person is speaking, the blue line is while he's singing, he or she, I don't remember. And this validated that while the person is singing, there is no buildup or no dangerous buildup of CO2 inside the mask, and the mask was approved for opera singers. But then COVID, we solved the problem of some of the problems of COVID. And they released the restrictions, so it wasn't used in the end. So that's a nice solution also for like a customized system, and not just lowering the price, but actually finding a solution which is not available. Okay, so cool. Everyone wants low-cost sensors, right? It's amazing. So no, there are challenges and pitfalls, as always. It's not a perfect system. There are a few papers discussing these different challenges. This is a paper I like because they're giving a very comprehensive overview. And I will try to mention the 3 main challenges. First of all, that it's not a straightforward process. Meaning, if you buy the sensors you are used to buying until now, it's a plug and play. It will take you, if you have knowledge of how to connect sensors, and if you did an experiment in the lab or in the field, usually it will take you roughly, I don't know, half a day, and you have a working system. When you are buying electronics, you need to solder them, you need to waterproof them. You have a lot of different steps, which are time demanding. But I would say once you have the solution, you figure it out, you invested the time in developing a working prototype, you can duplicate it in tens or maybe hundreds, and of course at a faster rate. And there is a learning curve. I wouldn't recommend it, for example, for a master student in the last half a year of the master, but I think it's a great tool, a great capability for technicians, for PhD students in their first or second year, if they are doing experimental work, not as a hobby. And can really solve and increase the measurements we are doing and provide better science. And this is a big problem when you're buying sensors from different companies from AliExpress. Sometimes you don't really know what you're getting, like you buy anything from these websites. So there's that problem. You can reduce the problem by, if you're buying sensors for local sensors from, like, let's say 4 or 5 leading companies that are pretty solid and you can trust their sensors. Okay, so now I want to build a system. What are the steps, the main steps I'm going to use? So first of all, I will try to understand if there is a need. It's nice, it's cool if you like to play with electronics, but we're doing research. So if there isn't a need, don't go there. Price can be a need, because once you reduce the price, you can put more measuring points. I would say 10%, if you're looking at a sensor which is 10% of the high-end sensors that you're using, go for it. If it's only like 20% discount, don't go there. It's not worth the effort. And then you need to identify the potential sensors while looking online. So accuracy and precision, like in every sensor we are using, are our main properties to look at. Look online if anyone else did it. Most likely yes. And then try to copy their design or advance their design, because it's allowed, and that's the purpose, that's the philosophy. Do some tests, try to understand how I'm going to manage the power, how I'm going to log the data, how I'm going to transmit the data, maybe to the cloud, maybe to an SD card, or whatever the needs are. Buy several sensors from several companies to just play with it. The sensors are cheap, so you can afford it usually. Do some calibration and validation, as always, and in every sensor you buy, also the high-end usually. Order the full set of sensors and hardware. Construct the system. More tests, as always, and preferable doing it in the lab and not while you're in the field. And then deploy it in whatever experiment you have. So these are like the main steps. And this is why I say it's not a straightforward process. But if you're doing it systematically, in the end, you can have a system that can actually measure in an accurate way. You have a successful solution, share it. And remember, it's only a tool. So like you can find students that are diving into building, and in the end, it's not research. So also that it's important to remember. Okay, so hopefully I didn't bore you until now with all the sensors and so, and I will show science that's being conducted with this type of sensors. My new lab is focusing on Earth atmosphere interactions, mainly on gas transport and water transport. And this is where I'm using my sensor. It means that I'm using CO2, local CO2 sensors, O2, temperature, relative humidity, soil moisture. That's like the genre of sensors I'm using. And one of the main projects I'm trying to establish now is greenhouse gas emissions from wells. Across the world, there are like millions of wells for water, for monitoring, for oil extraction, all types of wells, different depths, different radiuses, and so on. And some of them are being left uncapped. But once you have like a straw going into the ground, and this can be into the deep valleys, so it can be like maybe hundreds of meters, different gases that didn't see the atmosphere before suddenly can be emitted to the atmosphere. So in this case, this is the perforated section. If the water table is below this section, and the vapor zone suddenly start to provide or potentially provide gases to the well, and from there to the atmosphere. So there are a few studies that investigated this type of emissions from wells, mainly focusing on oil wells and methane. But usually it's just very hard to measure it. Like, how do you measure emissions from well? And if you can do it maybe for one well, and how you compare between wells. But once you're reducing the price, you can really try to instrument different locations. This is what I'm doing currently. You can see a local sensor unit, oxygen, CO2, air velocity, measuring the velocity of the movement inside the pipe. This is a 2-inch monitoring well in California, going down roughly 10 meters. All of the sensor unit is inside this 2-inch pipe. The cables are going to a data logger, low cost. and everything is sitting nicely with a nice solar panel on the well. And the entire system costs $400. Like now, once you can measure what is happening, $400 in a well, you can now duplicate for like 40, 50 wells, and still it's a reasonable price if you have like a nice research grant. And I will show you a result from one well using this low-cost system. This is a well west of Sacramento in California. The y-axis are oxygen, CO2, velocity going upward, outflow, temperature, and the fluxes. Now the fluxes are calculation of the velocity because we are measuring the velocity inside the pipe and we know the concentration, so we can estimate or quantify the fluxes. And you can see this is 4 days of continuous measurements. You can see times in which CO2 is increasing. It's not 0, it's 410, which is the atmospheric concentration. And all of these measurements are inside the well, yes? And you can see times in which the concentration are going from atmospheric in a matter of a few hours to 40,000 ppm, which is 2 orders of magnitude higher than what we have, 4%. And this is a significant sign of emissions. During these times, the well is emitting CO2 to the atmosphere in high velocities of a few meters per second. These are velocities that if you put your hand on the pipe, you will feel air going out. And if I'm using the CO2 concentrations and the velocity that I'm measuring, I can calculate the fluxes. And simple averaging, like one well emits during this 4 day emitted CO2 in the scale of 1,000 cars, according to average CO2 emissions per car in the US. Okay, one well, but think nowadays, like just in California, in the area I worked in, there were like hundreds of wells. So this can certainly be something which is important for overall scaling of greenhouse gas emissions.
From where high concentration of CO2?
So if you will approve my BSF, I will tell you. This is a main thing that we are trying to understand, and we have a few grants, a few proposals.
It's not an oil well.
So that
in an agricultural field?
Yeah, so we did the same, but not with continuous measurement, also for N2O, and we saw some emissions of N2O. It's highly location dependent. Like in agricultural areas, we see 4% of CO2. In the Dead Sea, I saw 500 ppm of emissions. So it's really depending what you have in the soil. We still didn't, we were not successful in differentiating if the source is the groundwater or the weather zone through the perforated section. But this is something we are aiming to test in different research. And this is one well. Like when the system is so cheap, we want to measure 50 wells, really in 50 different locations, and really trying to understand maybe the correlation between depth of the weather zone, groundwater changes, maybe chemical properties. So once you have this big data set, you really, hopefully you can try and understand what you're seeing.
What about atmospheric conditions? Did you check them, or
so this is
low pressure system, or?
So that's a great question. We have in the end 2 main objectives in this research. One is to understand the origin, or 3. One is to quantify, to say, okay, these wells are important or not. For example, if you just cap the well, you're reducing the velocity and you're reducing the emissions. So first to quantify, second to understand the origin, and third to understand the transport mechanisms. And there we have already a few published papers, but also here I'm not showing because of the time limitation. But yeah, in this well we didn't see correlation, but in most of the wells we are seeing correlations with pressure, atmospheric pressure changes, what is called the barometric pumping, thermal convection, like we see higher emissions in winter comparing to summer, and fast changes in groundwater levels. These are like the 3 main drivers. And why is it important? Because these drivers are advective drivers. Like if it was only diffusion, I would say, okay, 4% CO2, but it's moving very slow. Once it's advection, it's like shooting the air outside. This is why we see velocities in the scale of a few meters per second. Highly site dependent, highly type of land use dependent, and these are the questions we are trying to address.
Know why the fluctuations are so steep?
You mean this trend?
Yeah.
So in other words, we saw, because this is pretty much the trend of the atmospheric pressure above, So it's correlated, and this is how we know the atmospheric pressure it's the driver. Here we don't have an answer. We know for sure this is accurate data, because if you're comparing CO2 to O2, two different sensors, you're seeing exactly the same trend, but opposite, meaning once we have an outflow event from the lower part of the pipe to the atmosphere, high CO2, the O2 is decreasing. Like we really see, and even the fast changes for a sec, this is not a second, it's like a few minutes, you can see in both sensors, and these are independent sensors. So the phenomena is real. Our explanation, we're still working on it.
It also looks like a daily cycle, no? That's 1 day.
This is 1 day. This is 4 days. So usually it's between 1 to 2 cycles per day. In areas, for example, in my main project at UC Davis was a type of MAR. So once we flooded an agricultural field for groundwater recharge, we saw 14 days of flux, continuous flux. So there are different mechanisms controlling. Let's say if the system is stagnant, no water level changes in the groundwater. So usually it's only the atmospheric pressure. If you're changing also the groundwater and changing the groundwater, depending on the scale. So this is the complexity of the system. But once you can actually measure it continuously and not just take samples for the GC, you can really at least try to think what is happening. And that's the idea. This is one well, and this is one site in California that we're installing now a few wells, and I want to also to bring the Bowman orchard that I think Shachar knows, but it's for a different seminar. And this is only CO2. A few weeks ago, there was a paper was published. This is a paper that the company published, but in a scientific journal. And they invented a small device that can actually now measure CO2, CH4, and N2O at a sub-ppm resolution. And this is a company that does only low-cost sensors. So this, for example, can be a game changer. I think you can put something like that in a pipe. You can get all three main gases, CO2, CH4, N2O, on a reasonable resolution. So we saw 5, 6, depending we saw emission from this well, like we saw concentration of 6 ppm N2O, because it's an agricultural field. So there's we estimate a lot of densification processes. So I immediately send the company an email. They're like, wait, it's just like a validation experiment, but it will be in the market 2024. So that's their estimation. It's a solid, good company. So if they publish it, I'm guessing it's going to work. And that's like a different scale of science for people that measure greenhouse gas emissions or do environmental research. Okay, another project, and I think I'll skip that because of time limitation. Or we have time? No, we have time. So in this case, it's a proposal submitted to the USDA. We are using a lot of the underground nodes, as I mentioned in one of the previous slides, connected to different sensors in an agricultural field. No cables, nothing. The farmer is doing the same procedure as they used to do, it like doing without the experiment. And all of this data from a lot of different locations, which you can do a lot of different locations because the system is cheap. It's being transmitted wirelessly to a hub, and this is step 1. And everything is being pushed into a real-time model, crop model, with the goal of optimizing in the end nitrogen and water efficiency. So that's another nice example. This is only on the proposal stage. It's not something that we're doing currently. How you can use a lot of different sensors to optimize a model. And I will finish with the last thing that I'm working now. Like there is, in my opinion, there's like a big challenge of measuring CO2 and O2 in soils with a low cost. And this is something like I developed the prototype. Now I'm trying to validate it, and I brought a few examples. But in the end, these are the same sensor that I showed in the slide. But this is the sensor, yeah? And yeah. Cool. Great. So this is the sensor I showed in the slides. As you can see, in the end, it's electronics. Now, you can put electronics in the soil, it will not work. But with a simple solution, which is just like a regular 50 ml tube, You can add a hydrophobic membrane that can allow gas to go inside the container, but not water. You close it. You have a few waterproofing that you need to do on the cable. And suddenly you can put this in the soil and you can measure CO2 in a cheap way and in a way that can last for a few months. Now this is for the CO2. Same goes for the O2 sensor. This is not a new sensor. It's a sensor being used for a lot of years for oxygen, but the ability to, I hope it's clear. But the ability to integrate it in a system with CO2 is something which is, in my opinion, novel. And think again on the scales. Like if this system is working, you can measure CO2 and O2 in different depths in one location in the soil, in let's say $500. Now let's put it in like 20 locations in one field. Let's really try to understand the heterogeneity of the processes we are dealing with. Or maybe let's put now 200 across the country and try to understand maybe land use is related to different concentrations. And people are doing that. People are using, of course, measurement of CO2 in soils, but they're using only several locations because the sensors are very expensive. Usually they are not coupling it with O2. Like the power of O2 with CO2 is very significant because you can really try to understand, again, the mechanisms because you have these two very important parameters. And that's the main idea. And currently we are at the validation step in Sde Boker, just installing this type of sensors next to each other, seeing how the system is behaving, seeing that it's stable, the sensors are stable for several months, and then we deploy it in different locations. And you can see here results from a preliminary experiment. CO2 is the black line, O2 is the blue line, in a few days, and pretty much at least the trends are as expected, meaning when O2 is going up, CO2 is going down, and the opposite. But it's only from one experiment, and the real power is when you're comparing a lot of different sensors, and that will be the significant validation we are looking for. But it's all about the accuracy in the end. Like if you have a lot of sensors, but I don't know, they're like 50% off, it doesn't matter. It doesn't worth the effort. Okay, and that's my vision for part of my lab, which I call the Open Digital Environmental Lab. And I'm showing this slide because I want to give you a feel like, I'm guessing most of you are doing like experiments and give you some, maybe, I wouldn't say inspiration, but they give you ideas how you can utilize it. And if you want, we can discuss it later. So for red ozone measurements, we can do cheap solution to measure different properties, as I mentioned, in my slides. All the area of how you, like the brain of the system, how you measure the sensors, how you log the data, how you transmit the data. There's so many solutions that I didn't invent that are existing in the web, and you can utilize these solutions. Atmospheric measurements, this is an area which is still challenging because of the high frequency that you need to measure some of the parameters. So there it's not like a straightforward solution yet, in my opinion. Flux chambers, the use of flux chambers, as I showed, at least for CO2 is something which it was validated. For the other types of greenhouse gases, in 2 years with the sensor that I showed, it can be also a great solution for the other type of gases. In aquatic measurements, so here the main challenge is to take sensors and waterproof them so you can submerge the sensor. And this is another effort that we are doing. Some successful, like temperature is already successful, CO2 is successful. Other type of gases are problematic because of solubility issues and pH correlation and so on. We have a lot of, in our institute, like different bioreactor experiments. So there you can also just put a sensor and really understand from the engineering perspective what is happening during the process. You can mount these sensors on drones, not my expertise, but a lot of papers are published about that. And I'm happy that this vision was also published only as an opinion note, but in this short opinion, I'm showing how we can use these sensors to really change how we do science. One of the key points is that in the end, it's also a psychological issue. Like a lot of us think, it's cheap, it will not work, but suddenly it works. So, and that's one of the barriers. Okay, so like the main points. Think about it. From 1 point measurement, you can go for 10, sometimes with a similar accuracy and with the same price. You don't need to be an electrical engineer. You just need the time. And I'm saying just because it's a problematic resource, I know, and motivation, and because it's not a straightforward process. And I would ask you to think if you're measuring things, parameters, what would you like to measure? And we can discuss it afterward. With that, I want to say thanks for, these are the main collaborators in the projects I showed during my slides, mainly from, of course, Deboker and from UC Davis. And give you the stage for questions or whatever you want to comment. Thank you.
Question? Thank you.
Yes.
Just wondering, when you had shown data with high concentration of CO2, what kind of, is it calcium carbonate, or maybe the groundwater, like cola, or maybe situated with CO2? There's something unusual in that?
So it's something that I always like people are asking me for good reasons. It's the next step in the research. One of the things we want to measure is just lower CO2 sensor inside the groundwater and see what's the concentrations inside the groundwater to see if it can explain these high concentrations that we are seeing being emitted. If it's like a lower concentrations using, for example, Henry law and so on, so most likely it's from the Vedor zone. If the concentrations in the groundwater are very high and can explain these 4% CO2 concentrations, so most likely it's the groundwater. But that's our next step.
Another question
Yeah.
is, I mean, all sensors, which I understand they're quite relatively simple, like CO2, oxygen, methane, temperature. Did you have a chance to think or consider sensors that would characterize aquatic area, aquatic phase, like measuring absorbance, optical absorbance, optical fluorescence emission? I mean, there are some sensors, but generally they're much more expensive. But for the others who are dealing with water, they might be very important. Because they make give idea about chlorophyll or about organic matter or CDOM or whatever.
So it's very like I want to go there, but in the end, I need to focus because it's like a different field that I have no clue. But there are people working on it. There are like, for example, low-cost sensor for cyanobacteria in water bodies. There are low-cost spectrophotometers. It's like a different. There are papers. So first of all, if you want, I can send it to you. But it's like almost transition into a different. So yeah, I have a few projects, but I'm only like the side person, not the leading person.
I wanted to ask about the Decagon volumetric water content. From what I know, this kind of sensor work with the transmission of kind of electromagnetic wave and receiving. And I can understand the other sensor that you operate that work with output of analog or digital outputs. But if something emits electromagnetic waves, you need something to generate it. And from what I know, Arduino, maybe I don't know enough, but it's not have that function. So how you use the Decagon sensor, the volumetric water content?
That's where it works. You compare like sensor to the same soil connected to a CR1000 to an Arduino-based data logger. I don't know about exactly how the sensor works in that specific case. I just know it works while you compare it. I would say that there are specific sensors that will not work. For example, thermocouples, you need another component between the low-cost data logger and your thermocouple. If you're measuring redox potential, you need also to develop a solution because the system is not robust enough. but there are solutions online. Like there are people that measuring redox potential using low-cost data loggers, and they're showing how they did it and why it should work. So there are solutions.
Your experience with the varied sensors that have malfunctions or something like that, how כמה זה נשאר החיישנים נשארים
Stable.
stable and working?
Yeah. So the experiments are new, so I can say they're stable for 3 months because this is the time, the duration that they were tested. And so maybe in like 9 months, I would say to you, okay, it's for a year, it's good enough. With gas sensors like CO2, there's the big challenge of drift. Like a sensor can drift with the accuracy. If the drift is an offset, so you can maybe correct it, but if it's just like losing the stability, it's a different problem. Depending on the specific sensor, and I would say that I had the same problem also with like expensive ones. I once put 2 different sensors, low cost versus the expensive one, and the temperature relative humidity outside, and for some reason the temperature relative humidity from Decagon stopped working.
You have problems like the system is stopped working, or some sensors stop responding?
There is always problems. Like it's not a straightforward process. Like when you can't, let's say if you need an experiment next week, don't go there. Go with standard sensors, because you build the system and then you test it in the lab for a few weeks, maybe outside, maybe submerge it.
Yeah, I was wondering about the strategy where you vary the system, and when you want to fix something, what do? You have to do everything, or put nothing?
Up to you, depending on the research objectives. Same problem with like high-end sensors. In the end, something which is buried, you need to decide what you're doing. So the example I showed you, everything is wireless. So we took a system 1 month after because it stopped transmitting. And then we saw that the coating of this node was not good enough. So water, because it's an irrigated area. So water came inside, although we tested it in a bucket in the lab, but testing in a water bucket for like, 24 hours is not like 1 month. We changed to a different glue. It worked.
Rotem wanted to ask a question online. Are you there, Rotem? You want to try?
Hi. Yes, I wanted to ask about. First of all, thank you. It was very interesting, and I think we have lots of application for that. And I was wondering if you can tell me something about the temperature effect on these sensors.
Yeah. So once you buy from, let's say, a good company which manufacture local sensors, it's still local, but the company is a good one. Usually we'll get a data sheet with temperature effects and also relative humidity. I don't remember the exact effect for CO2 and so. In the scales we are looking for, let's say in the well example, we are talking about 400 ppm to 40,000. So even if the end it's inside the well, so the temperature is pretty much stable, or there's like a few degrees change. So it's not a big problem. If you're looking in the atmosphere to see plus minus 50 ppm of CO2 per day changes, so that's a problem. This is why I also mentioned that like for atmospheric measurements with this low range we are looking for, it's still not there.
So if I want to apply it, I better make sure that it's in constant temperature anyhow.
Depending on the sensor. If you want to measure something, go to the data sheet of that sensor.
Yeah, okay.
See the behavior. Think where, like in every experiment, what are the environmental conditions that are expected, and from there try to assess if it's good or not.
Thank you.
Do they give some warranty for the sensors? Or
$20, you don't get a warranty.
Yeah.
No. Like the funny thing is that in most of my experiments, the electrical box for the data logger is the most expensive part in the system. Which in Israel, I don't know why, but these are very expensive, the electrical boxes. Okay, so thank you very much.
Thank you.
Pleasure.
Thank you.
אני מנתק הכל? סבבה.
כן.
תגיד, אתה התחלת את הפרויקט הזה.